We are very fortunate to have this conference here. As a byproduct of this fortunate conference, we also have a fortunate speaker, Mukund, and he will tell us about superstring partition function in AdS3 with my former student. Unlike usual announcements at the beginning of seminars, we will not be taking the speaker to dinner. There will be a regular dinner here. I think I remember to say everything.
Thanks, Nazi. It's a pleasure to be back, and I'd like to thank Vast and Hofi and Nima for putting together this 2-week marathon. But talk today will not have any direct connection with the matrices. It's sort of more in the realm of string theory and gravity. So this is some work I've been doing for a while now with Samir Murthy, who is here. So things I omit, then feel free to ask Samir about. And my postdoc, Christian Ferkrow, who's been with us for a few years now. And let me, since I wasn't quite sure on how to pitch this talk, on the one hand, I would phrase the talk as bringing coal to Newcastle, if someone knows what that phrase means. There are people here who thought about this subject nearly 2 decades ago, but I hope that say something. I'll try to frame it sort of more broadly, and hopefully there'll be some things that will be sort of useful to others as well. So I have sort of 3 broad motivations for this work. Let's see. One is, if you look at semiclassical gravity, 3-dimensional anti-de Sitter space-time, and look at the spectrum of fluctuations, a lesson we learned a long time ago, back in the 80s from the work of Brown and Heno, is that while there are no physical propagating gravitons in 3-dimensional anti-de Sitter space, there's a spectrum of boundary gravitons. So if you do the one-loop partition function of Einstein-Hilbert theory in AdS3 gravity, you see that there is the partition function gives you boundary graviton data, which organizes itself into a Virasoro vacuum module. This was first pointed out in context of path integrals by Maloney and Witten, and worked out explicitly by Guillaume B. Maloney and Witten. Semiclassical theory, Einstein-Hilbert theory in AdS3. If you have some string theory, which has an AdS3 factor, you'd expect that the string partition function should also reproduce this in addition to all the higher stringy modes, which will be present in that theory. So we should see this from the spectrum of string theory. Simply because it, as a corollary, contains semiclassical gravity within it. And in canonical quantization, if you just canonically quantize strings on AdS3 times some internal space, very famously, in the very first paper on the subject, Gigan, Kutuzov, and Seiberg showed that that string theory has in it the boundary Virasoro generators as of physical operators. So in some sense, what I'm going to say sort of should follow, but what we'd like to do is see this directly from the string partition function. And the string partition function itself was also worked out nearly 2 decades ago in a nice paper by Juan, Hiroshi Oguri, and Son. And so a lot of the work for the first part of what I'm going to describe, which is in the context of the bosonic string, is just repackaging their data to make explicit where these boundary gravitons are in that calculation. The second part of the talk, which is what we are really after, is to try to extend this to superstrings and recover both the boundary supergravitons and test some string dualities. I won't get to the testing of string dualities today, but I'll outline some issues in getting to that discussion, which we've been encountering, which suggests some interesting subtleties with applying GSO projection and constructing string partition functions for superstrings. So some parts of this discussion are not fully fleshed out by us, but I'll explain what we've been able to do so far and where we're having trouble. Neither of these was our original motivation. Our original motivation was something slightly different, but as you'll see, post facto, that's a nice corollary of what I've been saying here, which was in the last 4 or 5 years, in various groups have been trying to understand the thermodynamics of near extremal black holes and showing that in the near extremal limit, black holes behave as ordinary objects with no macroscopic degeneracy. This was originally worked out in the context of BTC geometry by Maxfield, Turiachi, and Ghosh, and properly put in place in this right framework by Turiachi and Eliasiu. So we'd like to extract from this calculation the thermodynamics of near extremal BTC black holes. And show that the partition function scales like at low temperatures, t to the 3/2 times the classical exponential of the classical Bekenstein-Hawking answer, even at finite string tension. In particular, when the radius of the AdS curvatures go in string units is order 1. Not necessarily 1, which is not explicit. So away from what I will call the tensionless limit, you should see that this is true, and we'll see that the corollary of just seeing this boundary class. So with that motivation, let me say where we are going. So for the first part, I'll just talk about the bosonic string, which is the sort of setting ground for where we are. And you'll already see the recovery of the Virasoro vacuum character and the last statement I said. And in the second part, I'll sketch out the story for superstring. Any questions so far? Yes, sir.
I'm confused, but that's the t to the 3/2 that comes from the super Schwartzian?
So here, this t to the 3/2 is from it comes from the super Schwartzian if I was embedding it in the superstring. And sorry, in the superstring, it's not t to the 3/2. The super Schwartzian, there are also fermionic zero modes. For the bosonic theory, this will be 3. For non-supersymmetric case, it will be 3. I'll show you what we can get for the superstring. It's a bit more complicated for reasons.
My question was garbled, but I was trying to ask if that was the factor that usually comes, that in some other approaches comes from the Schwartzian.
It is indeed the part that comes from the Schwartzian, yes. Okay, so let's start with bosonic strings. And for the discussion, I'll just want to study bosonic strings on AdS3 times some compact space X. I will not specify what X is, apart from assuming that there's a unitary CFT describing X with an appropriate central change. For AdS3, I'm going to work with the Euclidean geometry. So if I was writing a semi-classical metric, I'll write the Euclidean metric. And I'll take the Euclidean time and angle to have not just the usual angular periodicities, but also identify the Euclidean time with a thermal period and the angle with an appropriate chemical potential. So that what I have here is the usual cylinder with a periodic identification and a twist by mu beta. Okay, so the boundary of this geometry is a 2 torus, and that 2 torus modular parameter I will call tau. And in what follows, whenever I write q, q will be e to the 2 pi I tau. I want to study string theory on this background. And in particular, I want to study the one loop string partition function. So I'll have a worldsheet theory, and I'll say something about the worldsheet theory with target space AdS3 in a second. But the string theory, the string worldsheet will also be a torus. And that torus modular parameter I'll call T to distinguish it from the modular parameter of the space-time torus. And I will use Z. It's e to the 2 pi IT in the right formulas. So what we have is a worldsheet torus, and we're looking for maps on this worldsheet torus into this AdS3 geometry times this compact unitary CFT. The first statement to note is that the worldsheet theory on AdS3 is an SL2 level K WCW model. Where K is the AdS length scale in string units. And this theory has a central charge, which is given in terms of K. And the central charge of this theory is 3K over K minus 2. And together with the XCFT, I'll make up a critical worldsheet theory with total central charge 26. This constraint, since I want X to be unitary CFT, this constraints K to be bigger than some number, slightly above 2, 52 over 23. But I'll take K to be bigger than 3 in what I want, for reasons that will become clear later. So for most of my discussion, I'm going to focus on K bigger than 3, and I'll comment on the limit K goes to 3 later. The K is large, then the semi-classical regime, and I expect that what I said at the top, namely the supergraviton, the graviton partition function should just work out. But we want to see what happens as we dial K away from the semi-classical regime down to small values. So there are many things I can say about this theory, and this was, as I said, worked out in early days of AdS-CFT by Nati and friends, and also by Juan. And there's some statements that one can say about the canonical quantized theory. This theory has a usual set of representations of which are both the discrete series and continuous series representations of SL2. And in addition, it has a set of spectrally float states coming from the fact that this target space is not compact. Okay. I won't go through the canonical quantization for this discussion. I'll try to write down the partition function and recover post facto the spectrum from there. So if you try to compute the string partition function, what we expect is the following. The string partition function is computing the spectrum of fluctuations around a single geometry. So a priori, it has no reason to give you a modular invariant CFT partition function. It's only a piece of the full CFT partition function. So when I write the string partition function, I'll think of it as a worldsheet quantity, which will be a function of the boundary modular parameters tau and tau bar. And this will be some piece of the CFT partition function, which in itself will get contributions from multiple samples, not just the thermal AdS3 geometry as I've written, but also modular images, various BTP geometry. So let's write down what the worldsheet answer is. And for this one, I'll tell you the answer because this was first worked out in the early papers. So what we expect a priori is an integral over the worldsheet fundamental domain in the complex T plane.
Shouldn't we take the exponential of the worldsheet partition?
So, thank you. Yes. So I'll say more why we should take the exponential, but yes, thanks one. This is indeed not the worldsheet partition function, but just it's the free energy. I should get a piece which is the SL2 WZW model partition function. And I'll be sloppy, I won't write down T and T bar, but it has both components, both holomorphic and anti-holomorphic component. A piece coming from the XCFT, which I'll not be agnostic about for now, but later when I go to the superstring, I'll specialize to special cases of X. And then the contribution from the course. Okay, so in some sense, this is a particularly simple example because we have a solvable WZW model for the AdS3 part, some unitary CFT we are assuming, and then we just have to do the ghost projection. So this guy is the standard answer. This guy, I'll just assume, has some expansion in terms of some states with some degeneracies. And what I really care about is what is the partition function of the SL2 WZW. And this, as I said, was worked out by Juan, Hiroshi, and so on. And it's given as follows. And I'll explain what these terms, what the individual pieces are in a second. Okay. So let me explain these pieces in this calculation. First of all, the three-factor is easy to understand. 1 over T2 is the usual answer you get from a non-compact direction. So this is coming from the fact that in AdS3, the radial direction is non-compact and acts like a new build mode, and that non-compact direction gives you, after the worldsheet integral, the zero mode integral to 0, 1 over T2. In the exponential, you see a sum over m and n, which are in integers. And that's coming from the fact that we have a toroidal worldsheet, which is trying to map into, there's a thermal circle. So we have winding states from both the spatial and temporal directions of that worldsheet torus onto the thermal circle in space-time. And m says how many times the circle is winding along the time direction, and n says how many times the spatial direction of the torus is winding along the time direction. So there's a classical solution coming from just the winding strings, and that classical answer is this exponential. So this is the same answer you would get if you were writing down the partition function for compact boson and with the target space. In addition, if we stare at this geometry, it's effectively a three-dimensional geometry. So this θ1 is the fact that there are three bosonic directions, and that's captured by this θ1. Okay, so θ1 is an infinite product. And the fact that you have fugacities y and y prime, y and y inverse, which are related to this u and m, which I'll tell you what it is in a second, is saying that of the three directions, two carry charge plus minus 1, and one of them is neutral. So the SL2 algebra is there's three generators, and corresponding to each of the three generators, you get one infinite product for the bosonic determinant. So this is just a one loop determinant from that geometry, and this prefactor is there to make sure that this combination is modular invariant. Okay, so one can compute this determinant, and this was worked out, I think, originally by Gavetsky, and then reinterpreted in the context of the sigma model by in this paper of Maldacena, Oguri, and so on from 2000, 2001. So this holonomy matrix, this fugacity UNM is coming from the fact that the torus, this worldsheet torus, is winding around this thermal circle, and these are given as combinations of the worldsheet modular parameter. It's holomorphic maps on the worldsheet into the target space torus. So in some sense, all the tau dependence, all the dependence on the space-time data is buried in these UNMs and in this explicit factor of P. And what we need to do is complete this integral and extract from it the dependence on tau and tau bar from the worldsheet answer. Okay. Any questions about this?
Your fundamental, this region F that you sketched should just be the fundamental domain for SL2Z, right?
It's a fundamental domain for SL2Z, that's right. It's smaller, but
It doesn't go to the real X, it's on. You should move the real X.
I should move the real axis down, yes. But I'm going to do something else in a second.
Sorry, can you explain this T2 notation again?
T2, sorry, I should, so T is the imaginary part of T. Thank you. Anything else? Yeah. Now, there's a standard trick to do this integral, which was first discussed by Polchinski, which is to use the fact that because when you do the winding sums, this answer is modular invariant. And M and N, which are the winding numbers from the worldsheet spatial and temporal and spatial directions on the target space circle can transform as a doublet under worldsheet SL2. So you can unfold this using Polchinski's tree to an integral over the half strip. At the expense of dropping the n sum, the m equals 0 term. And then you do so this is the integral for now for the so now the integral is over the entire strip. So what we get at the end of the day is some integral from the worldsheet, which is done over the strip, and you can just set n to 0 in this integral. But you're left with the m sum, but that is easy to interpret because the m sum comes with the fact whereas m times beta, it just says that the worldsheet computation doesn't give you just the contribution from single strings. It multi-particles the string answer as is appropriate for a statistical count.
Sorry, can you explain why you set n equal to 0?
Why I said n equals 0? So this integrand is modular invariant. M and n transform as a doublet under worldsheet modular transformation. So you can use that modular symmetry to start mapping this domain of integration down into the missing part of the keyhole. And at the end of the day, you can see that you can trade one of the sums, the n sum, for filling out the rest of the keyhole into the strip and drop that sum. In fact, this is not just true for the torus, it's true for any string amplitude or arbitrary genus. You can always trade it into one answer because finally, what you expect from a thermal sum is that you should get something that looks like taking a single string configure answer and then multi-particling as you would do in quantum field theory. Okay, and this is really explicitly making precise that statement. So at the end of the day, we just have to look at one piece of this answer, which is the term coming from m equals 1, and then the rest of the sum is basically think of it as the single string free energy, and then taking the sum over m takes the multi-string free energy, and hence what Juan said earlier, that if I exponentiate that answer, I would get the worldsheet piece of the worldsheet partition function. Okay. So with that said, let me now finally give you the expression for the single string free energy in the bosonic spin. And this expression, I'm just going to write it as an answer in terms of the boundary data. It's convenient to introduce an auxiliary parameter, basically Fourier transform to remove this 1 over T2 in the denominator. Square root. expanding out all the pieces of relevance and writing out products so that you can see where we'd have to combine comes from. So this exponential is just repurposing this exponential up here, and the k shift to k minus 2 in this factor here is coming from the fact that you get contributions from both this phase down here and the binding sum. And this is just the expansion of eta over theta. At this point, things look fine until you realize that you have a choice. You have to do the following. That in this extended strip, if I take q, the absolute value of q is e to the minus beta. I can take this to be less than 1. The absolute value of q is e to the n was bounded, but can be bigger than 1.
What is zeta again?
Sorry, zeta is, this zeta is an auxiliary parameter which I use to Fourier transform this 1 over T2. I don't want to have a T2 there because I want to do the T2 integral. So I have done I've introduced a Gaussian variable so that the width is now 1 over T2 instead of T2. So that's just a trick to do the integral. I'll do the zeta integral at the end. We'll do the integral of the worldsheet moduli first, and then do the integral of zeta. You will later see that zeta plays the following role. A priori, there was no reason to expect continuous series representations from this formula. When you're done with the integrals, and as I'll explain in a second, this zeta will transform into for the continuous part of the spectrum, into the continuous series label. So this integral hides both the discrete series and the continuous series and their spectral flows. I first explain the spectral flows and then explain where the continuous series comes from. Is this clear so far? See, I can choose the temperature to be whatever I want. So everything here seems fine. So I've assumed this to be unitary CFT, so there's nothing funny in this z of x. I see some nice factor here. This is just Q dependence. There's nothing to do with the worldsheet integral. I can pull it out. I've just kept it here for now. I just have to expand this infinite product, and I could imagine doing the integral term by term. As Maldacena, Oguri, and so on noticed, the problem is this piece of the theta function, the piece that comes because one of the states has charge -1 in SL2. And that can hit 1. As a result, in this domain of integration, you have a series of poles. Whenever Q inverse times z to the n, it's 1. Okay. Long story short, the residues of those poles will pick up the discrete series states and their spectral flows. But you'll be left with a piece of the integral that's not just the residues. And that's the continuous series, and therefore zeta is a label for the continuous series representations. Okay. So
This was what you just told Natalie, but what was zeta?
Zeta was introduced at this point just as a trick to allow me to do the T1 and T2 integrals by taking a Gaussian of width T2 into a Gaussian of width 1 over T1. So at this point, it just somehow. auxiliary integral.
Except you've got zeta in a lot of places as far as I'm concerned.
This is the Fourier transform. And zeta squared T2, when you do the integral over zeta, will give you beta squared over zeta T2.
Isn't it zeta also in that infinite product?
No, but this is my quant problem. This is Z. This is Z.
Ah.
Yeah.
Okay, sorry about my font. So, let me interpret this factor first before I then do something more. So this factor already gives you something like a 1/1 minus q. 1 squared. This is high, yes.
Okay, so earlier you mentioned there could be pole for the last term.
Yes.
You have an infinite, if it's an infinite product, so you probably will have infinite number of poles.
Yes, I will have infinite number of poles.
Okay.
Yes, I'll get to the poles and I'll tell you something about them. But first, let me say something about this factor. So I already have a 1/1 minus q squared factor. This you can already start interpreting as the action of holomorphic and anti-holomorphic derivatives on the boundary towards del and del 1. So this has the right structure to assemble into 2D CFT characters. Okay? So just bookmark that for a second, and now let's answer that question. So there are infinitely many poles. So in fact, the right one strategy to do the integral is the following: is in this T2 plane, you break it off into domains. Between beta above beta over 2 pi, between beta over 4 pi and beta over 2 pi, and so on and so forth, and isolate the poles and do the integral in each pixel. When you do this, I'll use W to denote the domains. So W runs from 0, W equals 0 is infinity, W equals 1 is beta over 2 pi. So think of the domains as beta over 2 pi. We'll get a sum over W, which is the sum over spectrally float sectors. And if I expand the infinite product, I would get some factors here, which I will write as which depend on some yes,
Basically, interpretation of the partition function before you integrate over zeta.
yeah. So before I integrate over zeta, we might as well go back up before there, and we're just doing the worldsheet modular integrals. That physical interpretation should tell you what are the contributions of various states to one loop fluctuations around thermal AdS3. So they would exponentiate after multiparticling into a piece of the partition function of the space-time CFT, the boundary CFT, but only a piece. If the story was complete, if this was the only saddle, it should have honestly given you a modular invariant answer, which you should have interpreted as a boundary CFT partition function after exponentiating. That can't be true because we know there are other saddles in this. For already in semi-classical gravity, we know there are other saddles. So in this case, if you sort of forgot about all the stringy states, and you'll see in a second what that means, we basically take K very large and keep the hierarchy between string scale and ADS scale present, then this whole answer should just collapse to the Maloney-Witten answer. It should just give you the boundary gravitons and nobody else. That we'll check whether that is true or not, or whether there's something else that survives the limit. What you can check without summing over other saddles is that this can't by itself give you a modular invariant partition function ZCFT tau tau. That's what I can say about the, but you had something else in mind?
Well, the answer you gave is much more detailed than what I wanted to hear.
Yeah.
If you just look at the integral of the function of zeta,
Yes.
and you perform the integral of the T1 and T2,
Yes.
is there a physical interpretation of this answer? For example, is this the microcanonical ensemble because zeta is it's kind of conjugate to beta or something else? Okay. What is the question whose answer? What's the
Yes, please
question
go
whose
ahead, sir.
answer is the integral of the T1 and T2 for this theta?
Right, sorry.
So it's true that zeta it multiplies beta, but the temperature beta also appears complicated.
Yeah.
So the physical meaning of zeta is really, remember that all wave functions in SL2 have roughly looks like e to the j times rho, where it was it's that j that is beta is the j. So what it will implement is the equation of more. It's not exactly the space-time unity, but
Okay. So I've expanded this integrand. I have broken up the domain of integration. And then before doing that, and so I have a series of answers from each domain, each of which will depend on what level I'm raising SL2 part, which is basically the powers of Z that I get from this expansion. That's basically saying how many oscillators are acting from the SL2 and what the internal CFT is doing. That's this power of Hx. And if you do the integral, the T1 integral does what it always does, it imposes level matching. And T2 integral basically picks out physical states. What you will find is you'll find an answer which is, I'll write as a discrete contribution plus a continuous contribution. And let me say that this discrete contribution you should think of as residues of the poles. And this continuous contribution still involves zeta integral and with a density of states, which is, let me say, given by Rho. And the energies of these states are given by yeah.
So this is in the modular space integration, it's a two-dimensional integration.
Yes.
But you have simple poles, I guess. But I think usually just a one-dimensional integration, you will pick up the residue, but it's a two-dimensional integration, how do you get?
Yeah.
You will get singularity, right?
Yeah. So I'll tell you what happens. So we have poles everywhere. The Z integral, the real part of Z, which is the T1 integral, will just give you level matching. I will tell you the phases
Oh.
are equal. So let's do the point particle example and you'll see what the difference is.
Oh.
So when I've gone through the unfolding and written the integral here, this is exactly like the usual bubble diagram in point particle, except there's one new thing in the string theory, which is level matching constraint. And that's always given by the integral over the width of the strip. The integral along the height of the strip is simply the integral of the Schwinger parameter, which tells you what the physical states are. They capture the spectrum. Okay. And that's why you see that beta goes with M, because in the multi-string configuration, the multi-particle configuration, you wind around M times around the thermal circle.
I think the reason he was asking perhaps was that before you talked about poles in tau, but this is really a pole in zeta. It comes after doing the tau integral.
Well, there are poles in, that is true. That is true. So I have done multiple integrals here. Yeah. So and then the final residue calculus I do is just on the zeta integral, which is what I'm using to proceed to talk about residues.
Okay. So basically, one integral, the real part, it just give you some delta function, give you level matching.
Correct.
Yeah, and the other one pick up the pole.
Yeah.
Yeah.
Let me write out just this piece because this is the most interesting piece. And I'll write it down at low levels, so you'll see what's happened. I've folded in all the factors of Q's. So now in the discrete sequence, I'll get terms of this time. This is really what we're after, and you'll see why. So this is the answer from a single string configuration. You see the answer has a piece which is purely chiral, which is purely either left or right moving, and then pieces which are mixed right, left, and right. Let's interpret each of them separately. So if you have a term of the form QQ bar, Q to the H, Q bar to the H bar over 1 minus mod Q squared. This term is a contribution from a single string to, it needs to be multi-particle and exponentiator to get the answer for its contribution to the CFT partition function. And this would give you some Verma module for some CFT primary of weight H bar. Okay. That's the right answer because this says that you have a single string state, primary state of weight H bar, and then you activate derivatives, and then you just multi-particle derivatives. What is special is these two guys. Q squared over 1 minus Q, which is of course nothing but Q squared plus QQ. And you can interpret this as a module where you act with L minus N of the space-time once. These are single boundary graviton states of the space-time CFT. And this will correctly multi-particle allow wherever geometry Malonian, for example, to give you the Virasoro mode vacuum character. let me write the zeta q. We'll get the we'll get the 0 point energy wrong, but that can be divided over. So indeed, you see that the spectrum, when organized correctly, so most of this is not new. Most of this analysis was done by Juan and friends. If you reorganize it to make it explicit, you see the boundary gravitons very explicitly in the calculation. And everybody fits nicely, all the states, including the continuous series representations, fit nicely because of these factors into modules of the appropriate boundary CFT. And this is the story where I assume that this internal CFT X doesn't have any symmetries in it by itself, because those would additionally give me additional chiral states. Yes.
Can you say what these boundary gravitons are in terms of the SL2 cap model representations?
Actually, you say it in your paper.
I said, okay.
But yes, so basically they are like, they're in the discrete series, and you can get them by acting with a certain J0. I can tell you whatever, but
The space-time J minus.
yeah. That's
The internal CFT is X,
yeah.
origin CFT as opposed to state.
Yes.
Also depends on T. When you do the integral over T,
Yes.
don't they contaminate this answer?
They do. They do. That's why I put them here. But I only wrote down for you the leading piece here. And everything which is coming from the internal state, assuming that the internal CFT does not have conserved currents, doesn't have marginal operators, contributes here. So they contribute, but their energies are very high from the space-time point of view. Their energies are ordered to K.
And K is the K of the SO2?
K is the K of the SO2.
It's not the same form.
It's not the same form? Oh, no, sorry.
Now I understand everything.
Yes, now you understand everything. But there are exactly, let me say something that will be helpful. The piece that's universal is this piece. This piece actually has a nice fact. It comes from the states with excitation number 1, n equals 1. The n equals 0 state I've dropped here because that's the tachyon. The n equals 1 state gives you these 3. And in addition to the chiral states, you see a prediction that there is always a state with weights 2, 2. And everything else is heavy in this theory.
What is that Q2?
So what is a 2, 2? One conjecture, which I'm not 100% sure is true, is that it's a TT bar operator that's there in the single string spectrum, but they're not sure about it.
So strictly, you cannot really separate the first 4 terms from the rest. Because even if when you expand in Q, if you go to high enough order in the power in Q, it can be larger than.
Definitely. But if I organize the primary spectrum, I can ask you, what are the states which are low lying and what are the states that are heavy? You're completely right. In 2D CFTs, I never can do this because I can always go down in any given module. I can go down deep enough, and I can match with some other primary. Yes, sorry.
Yeah, but there's one comment to be made is that there are two chiral, there's a chiral and anti-chiral current.
Yes.
It just stand out, don't exist there.
Yeah.
That's what we are.
Exactly. Okay. Got a question, Edward? Okay.
So
Yes.
your space-time doesn't need to be your weakly curved.
My spacetime does not need to be weakly curved. Everything I say is true for any K. As Nadi pointed out, if K is not small, if K is not large, there is really no hierarchy here. But if K is large, there's a hierarchy. But otherwise, this is the answer.
Does the number in the exponent actually depends on the internal space?
It does.
Oh, okay.
So this number is something like n plus h minus the 0 point energy, which is somewhere here. But
But the CFT always has a zero.
the CFT always has a beta, so that's what we were after. And as always, with Blackboard thoughts, I'm well out of time, but let me say a couple of statements first. For understanding this Schwarzian contribution, it is what we have on the board is sufficient. Let me say why. You can use the following argument. So all I've computed for you is the partition function around formal AdS3. You can, and I haven't computed the full contribution, but what I've shown you is that the answers for the ZCFT contains the Virasoro vacuum module, plus stuff, and the stuff is gapped. With some twist gap. Of course, the twist gap is large, and K is large, but there's always a twist gap. If you want the BTZ answer, you can take this piece and do the S transform and read out what the BTZ partition function is. And if you do that, and this is not new, this is what was originally done by Maxfield, Turiachi, and Ghosh, you immediately recover. So, going back to your question, at any K away from 3, you will see that the string theory prediction is the universal Schwarzian prediction. It's T to the 3/2 from the one locator. Of course, what we can't get from the string theory prediction, and I have not talked about this, is this piece, but that piece just comes from the semiclassical. The S0, the semiclassical Beckens and Hawking formula, I have not tried obtaining for you here. Something special does happen for K equals 3. And for K equals 3, you find from the first spectrally twisted, first spectrally float sector W equals 1, you find new higher spin conserved currents, which are part of a continuum. This was noted about 7 years ago by Gabardial, Gopakumar, and Hall. The K equals 3 special, so this gives you Schwarzian prediction. BTC. Okay, begin. Okay. And at the hour mark, I can either stop there or I spend 5 minutes telling you something about the superstring. Up to you folks.
Conserved currents are they in a discrete representation?
They're in the continuous zone. They're the bottom of a continuum.
So these states are at the bottom of the continuum?
No. So Juan's question was about at K equals 3. There's a
Bottom of the continuum means a state with S equal to 0.
Z equals 0, yes.
It's a little funny.
It's a little funny. It's not clear that there's sort
I
of.
never really understand.
Yes.
So why don't you take 5 more minutes?
Okay. So you might ask how to generalize this to the superstring, and one can. So what we managed to do is to do it for. You can do it for various examples, and a nice class of examples to study is compactifications of type 2 or heterotic theories on various four manifolds. And what we have results for is the T4 case. when you study type 2 on AdS3 times S3 times T4, what you should get is a theory in 2D CFT, space-time CFT with 4,4 supersymmetry. I'll make a couple of observations about this kind of theories. One, nobody's computed the one-loop supergraviton partition function for this amount of supersymmetry. And there's a good reason for it. At this amount of supersymmetry, the one-loop partition function in just AdS3 gets contributions not just from gets contributions from multiple geometries. The calculation, as far as I know, was done in JT gravity recently by Heidman, Iliesu, Toriachi, and Zhao, but no one has done the direct heat kernel calculation in AdS3. The reason this happens is that with lower amounts of supersymmetry, the vacuum modules do not have null states. But with n equals 4 supersymmetry, the vacuum module has many null states. And so you get a infinite sum with contributions, with semiclassical contributions going like Q to the space-time central charge. Second, so that's what you expect to see a piece of the answer if you just look at the spectrum around thermal AdS3, not the full answer. Second, there's a question of what kind of states do you expect. So for T4, you expect that you get a piece of the n equals 4 vacuum character. Times 4 free current, U1 to the 4, a super U1 to the 4 contribution from the T4. There are arguments in literature which say that you don't get 4 free bosons and fermions from the T4, but actually 8 free bosons and fermions. The string partition function doesn't see 8, it only sees 4. Okay, so I can explain this to the experts what this is. And third, if you have a choice of what to compute, and what is easiest to compute is from the space-time point of view to compute the trace in an
Sorry, can you go back to the U1 to the 4th?
Yes.
U1 to the 4th for left and right mode, or only one of them?
No, both of them.
So when you say that there's an argument for 8, it's really an argument for 6.
16, that's right, that's right.
So you claim that this argument is incorrect.
I'm just saying that we don't see it from the string partition function. It could be that they're boundary state, that they're singleton modes, but the string partition function is unable to see. I'm just saying that the string partition function doesn't see it. I'm not saying that it's not there. So one could compute for the space-time, one could compute the trace in the NS sector weighted by R symmetry chemical potential, because the n equals 4 theory has SO2 R symmetry. And by shifting the R symmetry chemical potential, you should be able to change between inserting -1 to the F and not. And this should be respected by the following. You can compute the string partition function with either periodic or anti-periodic boundary conditions for fermions in the target space circle. So if you're doing the partition function with periodic fermions, you compute the usual. So this is space-time CFT. This trace is the space-time. And this is the worldsheet. Spin structure sum for type 2 and 2B. You compute usual left and right movers with different projectors and then combine them. However, if you put anti-periodic boundary conditional fermions in space-time, the spin structure sum is different. You have to use the phases that Attic and Witten discussed to make sure that you get the right spin structure sum for anti-periodic fermions in space-time. And you can check post facto from our calculation that the shift of the R symmetry chemical potential reproduces the Attic-Witten phases that you would expect for going between periodic and anti-periodic fermions. Okay. So those are the statements that you expect. And what I will say in words is that when you go through the exercise and write down, which I read for you, some early stage, the optimistic, I will get to the answer. So here is the answer for the type 2B integral before I introduce this auxiliary zeta parameter. There's the usual story in terms of the, I've written down the modular invariant partition function, unfolded to the strip. So there's a contribution from the bosons. So this piece is exactly the SL2 piece from before. This is the bosons from, so these are the bosons from the T4. There's some additional contribution of eta functions from the T4 and everywhere else on the fermions. This is the SU2 WZW model contribution. And then here are the contributions of the fermions after doing the spin structure sum and GSO predictions. So you either get an answer for the periodic case or for the anti-periodic thermal case. And you can check, again, doing the same exercise as here, doing the integrals, you can check that you can organize them exactly into super multiplets, reduce characters of 4,4 algebra, and recover the supergravity spectrum that people have computed in the 90s. So that works out quite nicely for the case of T4. We have a puzzle for K3. We seem to break supersymmetry when we try to do the same exercise where we just do the spin structure sum on the orbifold T4 mod Z2. And I think there's a subtlety in how we're doing the Z2 orbifold. Okay. So there's one comment I will make and then stop. I find this puzzling. And I'll say why I find this puzzling. In this paper by Nathi, Givion, and Kutosov, they made a very important observation about GSO projection of strings on AdS3 times S3 times T. Because both AdS3 and S3 have curvature, it doesn't follow the usual story of GSO projection where you take a world sheet n equals 1 theory and argue that the secret enhancement of n equals 1 world sheet supersymmetry to n equals 2 does not hold. It's also true that you have only 8 supercharges, you don't have 16 as in usual string compactification. So you need something to break the space-time supersymmetry. So they just constructed the right spectrum by showing that the GSO projection has additional projections. So not all the spins, the spin states are part of the full spectrum. Some half of them get projected out. Our construction was very naive. We just followed the usual rules of constructing modular invariant partition functions in target space and world sheet and then computed spectrum and got matched with supergravity. I find this puzzling because somewhere along the line we should have seen something go wrong. Nothing goes wrong for T4, but something does go wrong for K3. So on that note, let me stop and apologize for going a bit over.
So what's the physical meaning of the continuous spectrum part?
Continuous spectrum part?
Yeah. How could I understand on FT, for example?
Yeah, so there are many ways to say this. One way to say it is simply the fact that the target space here is non-compact. So just like in flat space where you have a continuous space, so you don't have any reason not to expect a continuum, so you do expect continuum. There's a secondary reason which was first argued for by Seiberg and Vision in their paper on the D1 D5 CFT. So what we're doing here is just quantizing the strings with just pure NS and S flux. And the dual CFT, let's say in the S dual CFT with pure Ramond flux, there's a small incident on singularity. So there's a propensity for the D1 branes, which we should see as an incident on the D5 brane, sort of to leave the bound state. And that mode is associated with continuity. So one expects that one turns on in the example I was talking about, a small amount of Ramond flux. You would stabilize that continuum and only get a discrete spectrum, but that's a different question from what we've been discussing.
Lots of questions. Interesting seminar. I think he will be here around, so you can ask some more questions. And we'll go to dinner with everybody. Be a big dinner. Thank you.